Hi everyone, welcome to Made Easy with me, and I'm Mona, and I'll be just explaining the chemistry lesson today. So this lesson we have already taken in physics. Mostly, we have some new concepts, and hopefully it's easy for you guys. I have done this lesson based on the choice of many people, and hope you enjoy. All right, so. Starting off, we have two things related to the word kinetic. We have first the kinetic energy and the kinetic theory. The kinetic energy is the energy of motion or the energy of moving objects. And the kinetic theory for gases is that they are small, hard spheres with insignificant volume. They move in a rapid, constant, and random way. The collisions between them are completely, absolutely elastic. What does all this mean? Okay, so this we already know, but the kinetic theory, is something new. So when we come and look at the particles of a gas in a certain container, the shape of the particles, they are spheres, like they look like circles. All right, they'd be like this, far away from each other. Okay, and they're small. And they have insignificant volume. It means they're so small to the extent that you cannot give them a volume. So their motion, how they move, is rapid, really fast. Constant means moving in straight lines in random. So one does not move in a certain calculated way. It's a very random way. So a certain gas particle would be moving, and it would just keep on moving straight and really quickly and randomly until it collides with an object and changes direction. Now, what happens when it collides with an object is that it's an elastic collision. An elastic collision is one that has no energy is lost. So each particle keeps its certain energy. So when two particles collide, what will happen is that they will hit each other and bounce back from each other. They would rebound, each preserving its own energy. They won't collide and keep moving together like what happens in a car accident. No, what happens is that it's the same as when you smash two balls together. What will happen is that they would come together and rebound, each containing its own energy, each still moving almost at the same speed. So that's it when concerning the kinetic theory. Now, what we already know is pressure. We know what pressure is. Pressure is a certain force applied over a certain area. So when it comes to gases, a gas pressure is the result of billions of rapidly moving particles in a gas simultaneously colliding with an object. So when you have, for example, when I take this marker and I put this marker in a container containing, for example, H2, what would happen is that those gases would exert a pressure on this marker, an exact pressure that can be measured. Okay, so this pressure is basically those little particles colliding with this marker and bouncing back several times, applying a certain force. Okay, that's gas pressure relating to one certain gas, not when we say we put it in air. When you put it in air, that's atmospheric pressure, because there are different kinds of gases all at once. If you put anything in a vacuum or an empty space with no particles of anything at all, there would be no collision and no pressure applied on the object or this marker. Now, atmospheric pressure is, for example, when you're standing here, there's a certain pressure that you cannot feel because your body is making that pressure rebound almost, okay? So atmospheric pressure is the pressure applied by the atmosphere or the surrounding, being now air. That pressure, when it's applied over something, is called an atmospheric pressure. And it was caused by the gases in the certain atmosphere you are in. So there is atmospheric pressure because the gases are held together closer to the Earth's surface by gravity. the farther you go from the surface of the earth, being the farther you go from the core, the center of the gravity, the less atmospheric pressure you will experience, because there's less atmosphere basically. And now, how do we measure atmospheric pressure? How did they come up with atmospheric pressure? It's something called a barometer. A barometer is something that it measures atmospheric pressure. What happens is that there's this container that has mercury inside, and there would be something that looks like a thermometer, but it's open at one end, and that open end would be in the mercury. I'll be posting pictures of that, like to this side of the video. So this barometer, how it works is that the thing that looks like a thermometer is completely empty inside. Nothing. There's a vacuum. No air, no nothing. Because if there were air, the air would push down the mercury, and we wouldn't have an exact reading or an exact measurement. What happens is that when you put it in normal atmosphere at 25 degrees Celsius at a fair day with no wind, alright, when you put it outside, what happens is that the gases would start pressing or applying the atmospheric pressure on the mercury, and what would happen is that mercury would be pushed down until it starts moving up to the vacuum where there isn't any pressure at all. So that the reason why it's not open from the top too, it's not like a tube, it's not like an open tube, is because if there weren't vacuum, if there were other particles, the particles would almost compete with the atmosphere or the air to, like, it would push mercury down too. Alright, so this is relating to gas pressure, atmospheric pressure, and the barometer. Alright, so pressure seems to have so many units, and I will be stating all of them, the ones that we have been taught recently. So what they are, the SI units of pressure would be pascals, kilopascals, millimeters Hg, and atmosphere. Hg being mercury. So the main one is kilopascals, which will be 101.3. I'll be writing them down. The other units are bar, torr, centimeters Hg, and psi. So psi is pounds per square inch. Okay, so that's what psi stands for. So let's write them down, like write each one. So let's say that we are given 1 atmosphere is equivalent to 100,000 pascals, which is equivalent to 101.3 kilopascals, which is equivalent to 760 millimeters Hg, which is equivalent to 76 centimeters Hg, equivalent to 14.7 psi, equivalent to 760 torr, equivalent to I'll make sure about the bar and come back to you. Alright, so I'm back. So all this is equivalent to 1 bar. So let me repeat those. 1 atmosphere is equivalent to 100,000 pascals, which is equivalent to 101.3 kilopascals, equivalent to 760 millimeters Hg, 76 centimeters Hg, 14.7 psi, 760 torr, and 1 bar. Okay? These are all the units that you might need, and conversion between them is very easy. You just write, for example, they ask you how many kilopascals are there in 6 atmospheres. So what my question was, let me write that down. How many kilopascals are there in 1 atmosphere? I mean 6 atmosphere. So what you're going to do is you're going to write that we have 101.3 kilopascals is equivalent to 1 atmosphere. If you have 6 atmosphere, you get x kilopascals. And what you do is you cross multiply. You multiply 6 times 101.3 equals x. The answer would be 606.18 kilopascals is equivalent to x. Okay? Now, how is kinetic energy related to temperature? So average kinetic energy is, so since you have so many particles and so many substances out there, and when you heat them, their kinetic energy increases. We know that from previous knowledge. You cannot count each one's kinetic energy because there are billions and billions of particles in a certain cup of water, for example, or a certain boiling pot of oil. Okay, so what you do is you take the average, and in each substance at a certain temperature, all particles are in a certain range. For example, when you're boiling water, most of the water is ranging between about 90 and let's say 100, and even more than that because they're starting to evaporate when you're boiling water. This is the range. You would find one being 91, 92, 90, 93, 100, 101. That would be the range. It wouldn't go greater to 200 and wouldn't be less like 1 because you are already boiling the whole amount of water. So average kinetic energy is you actually finding the average, not one, all of the whole thing. Okay, so temperature is the average kinetic energy, and temperature is usually measured in kelvins. So the the relationship between average kinetic energy and temperature is that and the Kelvin unit is that average kinetic energy is usually measured by the Kelvin units. All right, and they are directly proportional. When the average kinetic energy increases by 1, the temperature, the Kelvin unit would increase by 1 too. So they are directly proportional. If you want, I'll just erase some of this and write it down. So AKE, which is average kinetic energy, is directly proportional to the Kelvin unit. So when AKE increases, the Kelvin unit would increase. And when AKE decreases, K will decrease. Alright, that's what directly proportional means. Now I'll be explaining the 0 Kelvin unit. We have taken that in the beginning of at the end of the second semester in physics. I told you this lesson is very, very related to physics, except it's chemistry, because we are talking about particles, and kinetic theory is basically about particles, and chemistry is the study of particles. So there is no, as we know earlier, there is no upper limit to temperature. Temperature will keep on increasing. If it's a solid, it's going to become a liquid, going to become a gas, and then it's going to become a plasma. According to my knowledge, there hasn't been any state after plasma yet. Plasma is pretty new and up to date, so they haven't reached anything after plasma. But you can lower the temperature and take so much energy from something. Like, for example, let's say it's plasma now. We would take energy, make it into a gas, take more energy, liquid, more energy, solid, and keep on decreasing the energy or the temperature until something just completely stops moving. Like when we say that that solids, they vibrate in place, liquids move about freely, they have they flow, they don't vibrate, they flow, and gases move very freely, rapidly, constantly, and plasmas almost have the same movement as gases, and something that reaches the absolute zero, the least temperature ever discovered, okay, it would stop moving and it would have no volume at all. That's what they have discovered, and only a few elements have reached that. For example, helium. Helium has reached that temperature, but you won't find it in nature. They have done it in labs, but not normally in nature. Not even Antarctica can reach that. Had that question in class before. Like, Miss, is Antarctica that temperature? Teacher's like, no. It can reach -50 out there, -100, but it will not reach -273 degrees Celsius. So, let me write some things about the Kelvin temperature. So that would be -273 degrees Celsius is equivalent to 0 Kelvin. This is the absolute zero. I really like its name, absolute zero. So at this absolute zero, what happens is that particles stop moving and there is no known volume that has been reached at this temperature. Alright, so the coldest thing in the universe is a nebula. A nebula is an explosion of a star. When a star dies, it actually explodes really, really, really quickly. Since a star is a collection of gases, what happens is that when it explodes, it becomes super, super cold. It never reached 0 Kelvin. It reached 0.1 times 10 power -9. So 0.9 zeros and then 1 Kelvin. So, as I said, nothing in nature has ever reached 0 Kelvin, which is absolute zero. Something very close to that has been reached. So a nebula is a very interesting thing actually in science. You can read about it in page 424. It's figure 13.4. It looks really beautiful, but it's actually a dying star. So